So last time I proved the following two results in fact. So Theorem One. Suppose that K, well, A is semi-simple Artinian algebra. I will explain what it is. Artinian over K without nilpotence. So this means that dimension of A over so semi-simple is without nilpotence, and Artinian means, so semi-simple is this, and Artinian means that dimension of A is finite over K.
It's just finite dimension.
Yeah, but semi-simple finite dimensional is a different thing. Semi-simple finite dimension is when it is central, direct sum of central simple algebras. So it essentially means that you multiply it by algebraic closure of K and it becomes a matrix algebra. Okay, then A is a direct sum of fields. And Theorem 2, that if you have two K1 and K multiplied by K2, and Ki is a finite extension of a field K, then this tensor product is again semi-simple Artinian, so it's a direct sum of K, some fields again, K small I, assuming that K big I over K is separable. So I will remind a bit about this. By definition, an extension K over K small is separable. If the form trace so it's a trace of x, y. It's a bilinear symmetric form. Symmetric form taking x and y into trace of the operator x multiplication by xy over K small, where multiplication by xy takes, it's an endomorphism of K big over K small, which takes x, well, A inside K big and multiplies by xy. Well, you don't need that. It's not hard to see that this bilinear symmetric form is just, it doesn't depend, it depends only on the product of xy. So what we need is that it is non-zero for some element. For instance, for unity. And of course, that trace of unity, of me unity, is just dimension of x, of K, over K small. So it is, this implies that K over K is separable when the characteristic of the field is infinite, is zero.
Prime field FE separable. Every finite extension is separable.
Yeah, yeah. Because you can't have typically this. I gave example last time of non-separable extension, but the important thing that all separable extensions, their dimension is divisible by p for non-separable extensions. Otherwise, you would have this trace. But you can't have extensions with dimension of p over finite fields, because for finite field, x power p is equal x. Power pn is equal, well, power pn. So there is no such extensions. Yeah, no, finite fields are always separable. Because all extensions have degrees which are divisors of pn power. So, well, it's sort of obvious. Well, maybe it's not obvious, but anyway. Okay. So let me explain how there was last time I explained that without details. So today maybe I should explain this theorem in a bigger detail. So it's sort of obvious that if your trace of an element is non-zero, then you don't have nilpotent elements. So if trace of A, B is non-zero, then A is not nilpotent. Because if A is nilpotent, this matrix AB, multiplication by AB, is nilpotent, and nilpotent matrices have zero trace. So to deduce this theorem 2 from theorem 1, you need to compute the trace on the tensor product. So if you have an operator, so you have K1 times K2, and well, we are interested in trace of, say, so consider a matrix. Well, we have bilinear symmetric form trace. Trace is bilinear symmetric form on this space. It's a space with bilinear symmetric form. It's just part of linear algebra. Now, suppose you have two, just an abstract situation, you have space V and W with this with, say, bilinear symmetric form G, and here you have bilinear symmetric form H. So on the tensor product, V times W, you can define this tensor. There are vector fields, vector spaces over K. On this tensor product, you can define a bilinear symmetric form as follows. I first define it on the tensor factors, on the monomials, and then extend. So if you have V inside V, W inside W, big, then you have a vector W, V times W inside V times W, and consider another one, V1 times W1. So it's V1 is here, and W1 is here. In the same space, I define G, well, let's use some G, H, well, U. This would be a bilinear symmetric form on this space, U of V times W, small, multiplied by V1 times W1 is equal to G of V1 multiplied by H of W1. So if we fix these three vectors, it will be linear in V, because it's this expression is linear in V. So it's linear in each of the multipliers, in each of the tensor factors. In particular, it's by if you fix this vector, so you consider it as a function of first two variables, and the second are fixed, for instance, V1 times V2, W1. This is bilinear as a function on, say, these first two factors. And this implies that it is actually defined on the tensor product because of the universal property. If you have a bilinear form taking vectors from V1 or V and V, or V and W, here it's V, this is in V, this is in W. So if you have a bilinear operation taking values in this product, evaluated on this product, then it extends to a tensor product. So U is indeed a pairing, and then you do the same on the second pair of variables. So U is a tensor, it's a bilinear symmetric form. It's extended, I defined it like that, but then I extended to a bilinear symmetric form. Symmetric on V times W. Okay, and now we can write its matrix explicitly. It's not hard. And this matrix is called tensor product of matrices for G and H.
Actually, this argument applies to any form, not necessarily a trace form. So
There was nothing about trace so far. I didn't even, so I started from that, and I. Yeah, if you have two spaces with quadratic forms, their product has quadratic form. Thank you, yes. And this is how you write this quadratic form. But now I wanted to express this quadratic form by a formula. For different reasons, you might need it. So you have A and, it's G equal to GHJ, and H is equal to HLK in basis W L in W. Okay, so now you take a matrix which has square blocks. In each entry of, say, G. And in each of these square blocks, you put matrix H. So you have the first block is, say, the block number 1, 1. You put H here, Hij, and multiply it by G1, 1. Then you have a second square block where you put Hij, the same matrix, and multiply it by G1, 2, 1. Then you have this same square block, Hij, multiplied by G1, 2. Then you have the same, but multiplied by G2, 2. And so on. This matrix is a matrix. It's a matrix of this U in the basis W V I tensor WL. It's called tensor products of matrices. So it is like H I J multiplied by G Gij multiplied by H L K, and the matrix is indexed by Vi times so this is your basis WL. So if you think of this square matrix with this as this set numbering the rows and the columns, then these entries are in the relevant rows and columns. So if you have a column number associated with I, L, with a pair I, L, this is the first index, and the second index is J, K. This will be Gij, H, L, K. This is tensor product of matrices. Okay, now let's apply this to trace. And you will see that the trace of on the tensor product of two algebras is expressed by a similar matrix. So if you have so it's lemma, you have R. You can do it for any fine-dimensional K algebra, not necessarily a field. R. So the trace is well defined for any algebra, obviously. R times R1 over K. This is Artinian algebra. And you have G and G1. Okay, R prime and G prime are, these are trace forms on R and R prime. Then trace on the tensor product is equal to G times G prime, which was a form defined here. So this is this form. So it's, in other words, trace of the product x times y multiplied by z times t is equal to trace g of xz multiplied by g prime of yt. Okay, so you have proof is very easy. It's linear algebra. You have two vector spaces over K and two endomorphisms. So V, W vector spaces. And then you have rho and mu and rho endomorphisms. V and rho endomorphisms of W. This is the tensor product matrix. But then the matrix this you can write if you have an endomorphism of V and endomorphism of W, this gives you a tensor product of endomorphisms. So mu times rho is an endomorphism of V times W. This is given by functoriality of the tensor product. How we defined it? It's clearly, if you have, from the definition, it's clear that any endomorphism of V gives you endomorphism of tensor product, and the same for endomorphism of rho, just by functoriality of the definition of tensor product. And the corresponding matrix, the matrix of mu times rho is tensor product of matrices. Is tensor product of matrices for rho, mu and rho. Clearly. Because you can just fix one vector in V and then the corresponding, and look at what happens with this vector under your action, and this would give you a square matrix which is proportional to your rho, and so on. So indeed, if you have, it's the same argument. If you have, as for tensor product of bilinear symmetric form, the tensor product of endomorphism is given by the same kind of square matrix, which is tensor product of these matrices. And this implies the trace of rho of mu times rho is trace of mu times trace of rho. Look, you have this big matrix with square blocks, and the trace of each of these, the trace, only diagonal blocks contributes to trace. And the diagonal blocks are numbered by, they're all numbered, they're all obtained by taking the first matrix, say mu, and multiplying it by a diagonal element in rho. The first, so the trace of this block is trace of mu times rho, times the first element on diagonal of rho. This is against the trace of this block is against trace mu plus multiplied by the second element of diagonal on rho. You sum them up, you obtain a product of two traces. So here I wrote H, but you can write mu and rho instead. So let me do it for, so you have here mu, here you have mu, here you have rho, here you have rho, here you have rho, here you have mu, rho and mu. So this is lots of copies of the matrix for mu, which are all multiplied by scalars, by numbers which are equal to the corresponding entries of rho. So the trace is indeed trace of mu multiplied by the successive diagonal elements of rho. Okay. Now, if you look at what happens here with respect to this tensor product of two algebras, of two commutative finite dimensional rings. So you have R times R prime inside R times R prime. Then it's clear that the matrix of the multiplication by R times R prime is tensor product of multiplication by R times multiplication by R prime. And the same is true if you have two such vectors and multiply them. So this implies that the trace form on R times R prime is trace on R tensor trace on R prime. So the tensor product of these two trace forms gives you a trace on the tensor product. This again linear algebra. What is important is that if it was a tensor product of non-degenerate form is non-degenerate, for instance, because you can compute the determinant of this matrix, and it's a product of determinants of each of these matrices. So it's a trace of determinant of A times B is determinant of A multiplied by determinant of B. If you want to check this, probably the easiest is to reduce everything to diagonal matrices or upper diagonal, like upper triangle matrices. And then the trace is product of diagonal entries. But the diagonal entries are precisely so it's like you take product of so you multiply mu ij many times while you obtain non-zero. I'm slightly curious about that. I think what I wrote is maybe not true because it's somehow, maybe you need to take power here. Can you see this? So this, it's clear that it's non-zero, but well, it's obvious that the determinant of tensor product is non-zero if your matrices have non-zero determinants. So this is clear. But is it true that product of tensor product, determinant of tensor product is product of determinants? I think it's false. I think we should put some power here, because you see, you multiply this every time, so it is like nth power of. No, it's tensor product. Yeah, it can be. Yeah, but it's still non-zero. So let's do it as an exercise. So we have if we have diagonal matrices, diagonal matrix with the entries AI and diagonal matrix with BI, then this tensor product has diagonal matrices which is AI BJ for all pairs of I and J, and then the product for I and J of AI and BJ is equal to what? It's like a determinant of A power rank of B times determinant of B power rank of A, I think. Right? Okay, so it's R rank of B, rank of A. But anyway, it's not there. So I am done with this argument which I started last time, and I was a bit sketchy with it. The important thing is that if your Artinian algebra has non-zero trace, like say for a direct sum of fields of characteristics 0, then tensor product also have this property. And in particular, tensor product of two fields is a direct sum of fields. So let's compute some examples. So my aim today is to prove primitive element theorem, which says that every finite separable finite field extension is can be obtained by adding one element. So it can be generated by one element. It will be used a lot in commutative algebra. But it's a part of Galois theory. So now proposition. Consider this kind of primitive extension. So you have a extension of form K1 is K of t quotient by P of t, by the ideal generated by P of t. So it's a kind of primitive extension which you can have. And then K is equal to, it's just extension. Any extension of finite extension, any extension. Then take tensor product, K times over K small K1, and it will be equal to K of t quotient by the same polynomial P of t. Of course, it's this polynomial, so as I told last time, this quotient is a field if and only if P of t is a irreducible polynomial over K. This polynomial P of t is no longer reducible over K of t. So this quotient is no longer a field. But as we proved, it is direct sum of fields. But the proof immediately follows from the observation we did a lot already, that if you have M, a module over a ring, you multiply it by R quotient by I, this would be the same as M quotient by IM. So in that case, the R over I is this ring quotient by this ideal. So M is equal to K, and R is equal to K of t, and I is equal to P of t. You apply this formula, obtain this formula immediately. Okay. So this is an example when you can explicitly obtain tensor product of fields doing nothing. Yeah, I don't see why we need here monic polynomial. I think it's some, maybe it was just copy-pasted from a similar argument for rings, then you need this monic. But here it's completely irrelevant. Okay, so
It's not the case here because any ideal in polynomial ring is, so polynomial ring is principal ideal ring, so any ideal has this formula.
yeah. Well, maybe it's convenient to write it explicitly like that, and this is why I wrote it monic. Doesn't matter. Monic is polynomial with link infinity. It will be really important very soon when we do with rings, but for fields it's sort of overkill. Anyway, so we have consider now a special case of that proposition where you have so it's corollary. We have P of t is a polynomial in K small of t, but over K we have over this bigger field, P of t is equal to the product of t minus alpha I. So this means that P of t has alpha I. Well, I mean, it's a product of linear, so it has all roots inside this field K. Over K small, yeah. When I miss it, it's over K small. No, it's K1 is not a ring over K of t. I mean, sorry, K is not a ring over K of t, so it won't make sense to take the product over K of t. Okay, so then K big multiplied by K1 over K small, where K1 is like that, is equal to direct sum of several copies of K. And the proof is essentially Chinese remainder theorem. So it's a version of Chinese remainder theorem. So you have a P, so it's AI here. And then you have a map from this tensor product, K over K small K1 is mapped to direct sum of K numbered by AI. It takes T to, it takes polynomial Q of T to Q of AI. So it's well defined on K1, because K1, I remind you that is equal to K small of t quotient by P of t. So if you plug A1 inside of t, this becomes 0, so it makes sense. So it gives you a map to K. So this is a ring homomorphism. If we can prove that it is invertible one-to-one, we are done. So first, by dimensional reason, the spaces have the same dimension. So now we need to prove. Is there any notation for this map? Tau. The tau, so you have tau here and tau there. Tau is bijective. Okay. So you have, as I told you already, this tensor product has this form. So it's polynomials over K big quotient by P of t. And if you have a polynomial Q of t, which vanishes such that tau of Q of t is equal to 0, this implies that Q of t vanishes in A1 dot AN. Okay, here I didn't write it, that they are all they are distinct. I wrote it on the slide and I forgot to do it there, so all AI are distinct. Of course, since if we start with a reducible polynomial, then in characteristic 0, all roots are distinct, because otherwise you could take lowest common denominator with the derivative, and it will be non-zero. So for irreducible polynomials, all roots are distinct anyway, but only in characteristic 0. In characteristic P, the derivative can be 0.
The property of separability is how classically separable extension.
Only for, not for composites, only for primitive extension. Yeah. Yeah, but not every extension has this is a primitive. If it's not separable, typically it's not. Because theorem of primitive elements, that all extensions are primitive, it's false if you allow for non-separable extensions. So this classical definition makes sense only if for primitive. So you need to define it for composites. Okay, so if it vanishes in A1 dot AN, this means that Q of t is divisible by P of t, which is equal to product of t minus AI. I mean, this tau, what it takes Q of t and evaluates in all AI. So if it is evaluated in all A of I0, this means that this polynomial vanishes in all I, and then it is divisible. So this means that this map tau, we obtain that tau is injective. If something goes to 0 under tau, this implies that it is divisible by P, so it there's none so and then the tensor product is just K of t divided by P here by this by this proposition, yeah, here. Okay, so it's injective, and we need to prove that it is surjective, but we just count the dimension. The dimension of this is clearly equal to degree of P. I mean, every polynomial is equal to, you can use division with remainder, and every polynomial will be equal to, it's up to modulo P is equal to remainder, and remainder is precisely degree n minus 1 if n is degree P. So dimension of K of t quotient by P of t is equal to degree of P. And here we have also dimension which is equal to degree of P. So dimension, it's dimension over K, and dimension over K of direct sum of K over AI is also degree of P, because there are precisely n roots if n is degree. Okay, so this means that every polynomial is so this map is one-to-one. It's a version of Chinese remainder theorem, which says that you can find, if you have lots of numbers which are have zero, lots of numbers which are coprime, you can have a number which has a given remainders after division modulo each of these numbers. So Chinese remainder theorem, I can remind you. It says that if you have a1 dot an are coprime, it's integer numbers, then there exists n, and you have m1 dot mn are some elements in just anything. There exists n such that n is equal to mi modulo ai. And here we do the same, but with t minus ai instead of ai, and of polynomials. So it's similar. And you can have similar results for any field. Maybe we shall, for any ring, maybe we shall have it at some point. Okay. So there is an exercise. If you have p of t is a polynomial over q, and it has r real roots and 2s complex roots, non-real. So, of course, all complex roots go in pairs. Then you can take the tensor product, like we did. So q of t by p, or q of t by p, and multiply it over q with r. And I claim that it should be equal to a direct sum of SC plus direct sum of R. Yeah, dimension is good because this should have dimension degree of P. So C has degree, each C contributes twice to dimension, and each the complex roots go in pairs. So what do you think about this exercise?
Geometrically, it's clear. So we can consider this ring as a schema, as a number of points, and when we compute the residual fields in any root at any of these points, it will be either a complex ring or the real ring. The complex field, the real.
But why these numbers? So it's sort of clear that
the numbers of points is where this is called residual field.
residual field is for things like local rings. Don't see any local rings here.
What was the question?
Why this is isomorphic? Part of that we have, because we know that it is direct sum of fields. And it should be fine dimensional over R, because this is fine dimensional over R. So this is direct sum of fields. But why this is particular? So on the other hand, every field which contains R is C over R, because C has dimension 2 over R, and there are no other fields. So it's sort of clear that we have C and R and nothing else. But why there are S, C, and R, and not some other number? So what goes on with numbers? How you can see that the numbers are there? Yeah. Why? Why this? There are SC and RR. For example, you can take something like polynomial p is equal t squared minus or plus 3. Or plus 1.
Factors into the product of linear and of quadratic part.
Why? So anyway, this. Well, main theorem of algebra tells it over C, that every polynomial over C is a product of line, like one-dimensional, degree 1 polynomials. What next? And this, the MITI tells us about polynomials of over R, and not over C.
Degree, then it has real root.
Yeah, you can factorize it and obtain, but how it has, what it has, okay, yeah, you want to decompose a real polynomial into a product of quadratic and real, and linear. So if it has real root, yeah, you can always decompose it into a product of even degree polynomial and linear factor. Yeah, so if you have two conjugate roots, you multiply the corresponding linear factors, you obtain something real, because it will be fixed by complex conjugation, and this will give a real quadratic polynomial. Very good. So we decompose the polynomial into a product of quadratic and real, and linear. And what next? Yeah, we start with a real polynomial, and we want to prove that, well, I told about rational polynomial, but it's right. It's enough to prove it for real polynomials. So you can write here R and multiply it over R. Yeah, and then for, yeah. So Q of t multiplied quotient by P by this proposition, which I already proved, is equal to R of t quotient by P. So it suffices to prove that this algebra is equal to that algebra for every polynomial P.
So we have polynomial with coefficients in real numbers. Okay, apply to it a fundamental theorem of algebra as it was a complex polynomial. So we factorize it into the product of linear members of over complex numbers, possibly complex root. But we know that complex root go in pairs, in conjugate pairs. So those which are real, that's okay, we just leave them, and those that are in complex conjugate in complex conjugate pairs, we just multiply them, and we have the product of complex conjugate. I mean, like z minus a times z minus a bar. If we multiply them, we get a quadratic real
Yeah.
polynomial.
So you proved that every p of t over reals is a product of linear polynomials t minus ai multiplied by quadratic polynomials t minus t squared minus ct minus b.
And then we use this Chinese domain theorem to write the
Okay, though I didn't prove this version of Chinese remainder theorem, but you're right. You can do that, and this would probably one of the best solutions for this. Thank you. But there are other solutions. The easiest is probably just to notice that you would have, for each of these factors, you would have a field, which is degree 1 or degree 2 over r, and degree 1 field containing r is just r, is degree 1, and degree 2 field, two-dimensional field over r, can be only c. There's no other fields.
Actually, the version of Chinese remainder theorem that we need is the following. If you have a ring and a set of ideals in that ring that do not intersect, like that disjoint, then we can define the map from
This ring to a
from this
direct sum of quotients.
sum of quotients, and it would be an azimuth.
It would be surjective at least. Okay, thanks. That's good. Okay, and then of course you can have the same for every, not only a polynomial which is has a product of linear polynomials, but any polynomial. If you have a reducible decomposition of a polynomial p of t is a product of pi of t, where pi of t in k of t are reducible, then k of t quotient by p of t is equal to direct sum of k of t quotient by pi of t. This is the same arguments as we just described. Let's maybe make a break for 5 minutes. So it's 4, we can meet at 5. So we discussed this quotient by the ideals. Now let's, before I'm going on, I already defined algebraic closure. Algebraically closed field. It's a field which doesn't have any finite extension. So definition, K is algebraically closed if for any finite extension K1 over K, K1 is equal to K. And remark, this is the same as having all polynomials, all irreducible polynomials, degree 1. Because if you have a field extension, then, we didn't prove yet that it's this field extension, and this is actually false for characteristic P, that this field extension is generated by one element, but definitely you have a subfield which is generated by one element. So if you have K1 over K, finite, non-trivial, then it contains K of 1, contains subfield K2, which contains case K, and K2 is equal to K, the polynomials, which is generated by one element, quotient by P of T. And since that has no zero divisors, it has to be irreducible. This is something we had last time. So the irreducibility of this quotient is equivalent to P of T, the P of T is irreducible if and only if this quotient is a field. This is something we discussed last time. So if K1 is a finite extension, you have a irreducible polynomial which is not degree 1. Irreducible is not a product of two smaller degree polynomials.
Yeah.
So P of T is irreducible if and only if this quotient is a field.
This quotient is a ring.
Yeah, but if this ring is a field, if and only if P of T is irreducible. This is something we discussed last time. It follows from the, because this quotient is clearly Artinian, and then it's a direct sum of fields. But if it is, if it's irreducible, then this is actually a field because it has no zero divisors. It is irreducible if and only if this ideal is prime, and this equivalent to being maximal because of this classification of Artinian rings which I gave. Okay, so if K is algebraically closed, there are no extensions. And conversely, if you have no extensions, you can't have this quotient being a field. So there are no irreducible polynomials of degree bigger than 1. So there's a way of, this gives you a way of producing an algebraic closure. So you produce algebraic closure. You take K, add roots. So you take bigger field. Take K for all P of T irreducible. You take K of T quotient by the polynomial ring quotient by P of T, and repeat. and apply the sort lemma in order to obtain a limit of these extensions, which would give you algebraic closure. In fact, you can do it even easier, but it would take some footwork because it will be infinite. So you can just take a tensor product of all extensions. And so you take tensor product of all extensions over k small and decompose it into a direct sum of fields. And take a limit. This doesn't work properly because it's infinite dimensional, so it's not a good way of doing it, but just adding more and more roots and taking limits, so it will give you algebraic closure. So you do you just consider sequences of subfields, sequences of fields. You start with k, you embed it to k1, you embed it to k2, which all are obtained by adding more roots. By adding, when I say adding more roots, I mean this: if you take this quotient, then p of t has a root, t in this quotient. So this means adding a root to a field. You increase your field so that the polynomial p of t acquires a root. In that bigger field, p of t equals 0 has a solution t. So you take a field. If there are no polynomials, no reducible polynomials, you are done. If you have a reducible polynomial of positive degree, you add the root of this polynomial using this procedure. Then you add more and more roots, and you take the closure of this family, and you apply the Zor lemma in order to have a biggest possible algebraic extension of K. So your algebraic extensions are ordered by embeddings. And you consider, obviously, if you have a increasing chain of algebraic extensions, the union is also an algebraic extension. And then you take the biggest possible algebraic extension, and it has, if there exists a polynomial which has no root in this biggest possible algebraic extension, then you can add it. So you obtain even bigger algebraic extension, which is a contradiction. So this maximal element in the set of algebraic extensions is actually algebraic closure. This is how it is done. Okay, am I clear with this algebraic closure? Good. Now I will, this is sort of a bit similar to what we discussed when we take a tensor product of a finite extension of Q with reals. So let's do it with reals are almost C, it's almost algebraic closure, so let's do it with algebraic closure. Theorem. So you have K as a field, and K bar is algebraic closure. And you have a separable finite extension. Then K big multiplied over K small with K bar is direct sum of several copies of K bar. This is more or less again Chinese remainder theorem, except that we didn't prove that. So if we had K, if K were obtained by adding just one root, so if it will have a form, so if K big is P k small of t quotient by p, then we already have it. It is proven already.
Is the sum of the number of summoned is dimension of k big over k small?
Yeah, of course. But we already have it because then the polynomial p has all roots. It's a product of degree 1 polynomials in the field k bar, so we can take this quotient and use Chinese remainder. But this is not, we can't use it because we want to prove the primitive element theorem. We want to prove that every extension can be added by one root. So you can't use it if you want to prove it. Okay, so the first observation that so proof, step 1. Okay, so we can multiply k big, we can embed k big inside k bar. So there exists an embedding. This is because as you add more roots, so as I told you last time, every extension can be obtained by adding roots. It's a composite extension of primitive extensions. So every time you add a root, you can map the root, take the corresponding root in k bar. So every primitive, if every primitive extension can be embedded to k bar, so every extension can be embedded to k bar by taking successive primitive extensions. And then you take k multiplied over k small by k bar. It is equal to k, we already consider k big as a field in k bar multiplied by over k small by k. And then this is multiplied over k big by k bar. And this is a direct sum of fields because this is separable. So it's direct sum of ki multiplied over k big by k bar. Okay. So because this is because k big is separable. So it's sort of step 1 and step 2 on slides. Okay. And now we have the second observation is that step 2, k times over k small with k. So this field has at least it has at least two non-trivial summons. So it has its decomposition of ki. This decomposition is non-trivial because if p of t for the following reason, so you have k contains a primitive extension k, say k1, which is p of t, k of t quotient by p of t. But then p of in k, p of t has a root, which is t. This t is a root of p of t. has root t, which belongs to K1. So P of t is not irreducible. P of t is not irreducible in K big. So this implies then K big, which contains P of t, oh, sorry, it contains K of t by P, has their divisors. Because this is not irreducible because of that. And then K times K over K small has their divisors. Then this is direct sum of fields. And this number of fields is bigger than 1. So this direct sum decomposition is non-trivial. The final step is induction. So assume that we prove this theorem. So step 3, assume that theorem is true for K big over K small of degree less or equal than D. And we have now, or less than D. Now we have K over K small degree D. Then K times over K small K bar, it's contained, well, it's actually equal to K times K over K small multiplied over K big by K bar. But then this is direct sum of Ki multiplied over K big by K bar. The funny thing that all this Ki have smaller degree over K big. So degree, dimension. When I say degree about fields, this is the same as dimension. So dimension of Ki over K big is less than dimension of K over K small. This is because dimension of K times K over K small, this over K, is the same as dimension of K big over K small. This is tautology, essentially. You just replace you consider vector space and you increase your vector, you multiply, you increase your base field. So this is tautology. You have a vector space over some field and you you take a tensor product because dimension of V over K small is equal to dimension over K big, and multiply V times over K small with K big. So it's the same vector space over a bigger field, the same basis. So this dimension is clear, but then this is direct sum of Ki, so they have smaller dimension. And then you can use this induction by dimension. So this tensor product of Ki times K big is already known. They have degree less than D, so they are already known to be a direct sum of fields K bar. Okay, so this proves this theorem. Was I clear? Questions? I can repeat. So the idea is you need induction by degree because essentially because you want to do it for composite extensions, like adding more and more roots, and you know that when you add one root. But so we could do it with roots, but somehow it's more easier and more invariant to do with tensor product. So you, instead of taking tensor product with k bar, you do it in two steps. You multiply it by k, considering k big, consider it subfield and k bar. This will already split onto direct sum of fields which are smaller degree. And then you multiply these smaller degree fields by k bar, and you're done. It's the same as taking composites, essentially. Okay. So now I can do this primitive element theorem finally. This was the purpose of today's lecture. Okay, so now we're interested. It is something I mentioned last time, but I didn't really give a proof because it was already late. So last time we discussed the number of prime ideals inside this fine-dimensional Artinian ring. And I claim that it's finite and it's sort of obvious. It is sort of obvious, but let's do it more carefully. So last time we have a semi-simple Artinian. Well, it's the same as direct sum of fields. Then the number of prime ideals. And prime are the same as maximal ideals. In A is finite. So today I do a similar result, a lemma. You have a field K. And you have an algebra which is direct sum. So it's a field. And you have an algebra A, which is direct sum of several copies, finitely many, of K. Then the number of distinct subalgebras of A is finite. Well, this is about quotient algebras, but the proof will work for algebras, for subalgebras, for quotient algebras. The same proof will work. Oop. Yeah. It's terrible. Okay, so let's prove it. So you have E1 dot En as unities in the summons K inside this direct sum of K. Direct sum of K small. This is our algebra, and I take unities there. So they are all idempotents, meaning that this EI squared is equal EI. It's definition of idempotent. Now, if you have a subalgebra, if A inside A1 inside A subalgebra. It actually is, then there exists the idempotent E, let's call it, say, R, and call it ER in R, such that ER times, so it's a unity there, which acts as a unity. So ER times X is equal X for all X inside this subring. It was proven last time that every Artinian algebra contains lots of idempotents, and if you sum them all up, you'll obtain unity. So, well, every Artinian algebra is direct sum of fields, right? If it's semi-simple, it has no nilpotence, so this R is direct sum of fields, and then you have this sum of unities in all these fields in R, which will give you this kind of idempotent. Okay. So now we have this ER times EI is equal to EI or 0. This is because A is K plus K plus K. So if you have a unity there, and you have some idempotent, then the product is ever 0. This means that your idempotent is projected to this K by 0, or it's projected to this K by 1, and then it is EI. So it's true for all idempotents in this algebra. This implies that the number of idempotents, that all idempotents in A or in R are sum of EI J for some subset of E1, E2, and so on. So you start with idempotent, and you project it to K1, you project it to the first, to the second, to third, and so on component, and it maps either to 0 or to 1. So it is a sum of these projections, obviously. Okay, good. So there are finally many idempotents, and our R is obtained from idempotent is ER times A. So the number of idempotent is finite, and the number of subalgebras is the same as number of idempotents. So this is why there are finitely many subalgebras. Was I clear? So the main argument is just that every algebra which is semi-simple is Artinian semi-simple is direct sum of fields, and then it contains is generated by idempotents. In fact, last time it was opposite direction. I proved the existence of idempotents and used it to deduce that it is a direct sum, but it's the same. Yeah, sorry, I didn't prove the primitive element theorem. Let's prove it. So I will use, obviously, the finiteness of the finite now that there exist finitely many subalgebras. So theorem. Suppose you K over K is separable extension, finite separable extension. Then there exists x inside K such that generating K over K small. In other words, this K big is polynomials K small of T quotient by some polynomial, irreducible polynomial P. This is the primitive extension. Okay, so proof. Step 1. We have algebraic closure. And algebraic closure. And if you have intermediate subfield K containing K prime containing K small, and you multiply everything by K bar, then K prime is a subalgebra in K times over K small by K bar, which is direct sum of many copies of K, but finally K bar, finally many. So it's subalgebra. And there's finite number of them. There are finitely many subalgebras. So there are finitely many subalgebras if you, of course, if you start with, if you have infinitely many K prime intermediate, so K between K prime between, or Ki between K, this, and you multiply everything by K bar, this would give you infinitely many subalgebras between K bar and Ki times over K small K bar. And this sits inside K bar, direct sum of several copies of K bar. So if you pass to a tensor, you tensor everything with K bar, there will be also infinitely many intermediate subalgebras, which is impossible, as we just proved in this lemma. There are only finitely many intermediate subalgebras between this and that. So this implies that there are finitely many subfields between K and big and K small. Okay, so this was step 1. And let's, so it was characteristic 0. So step 2. Now we have K big considered as a so consider let R S be a union of all finite of subfields. Proper subfield. It's a union of all proper subfields. Proper subfields in K big. They're proper subfields, so it's a finitely many subspaces of codimension of positive codimension. So S is not equal to K big. Because every time if you have an infinite field and characteristic is 0, so the field is infinite. For finite dimension, for finite field, it won't. This argument will break. But if you have a vector space over a finite dimensional vector space over a infinite field, the number of subspaces is infinite, and in fact, for every finite collection of subspaces, it can't give everything. So the union of positive codimension, positive of finitely many positive codimension subspaces is not equal to a vector space. This is a fact of linear algebra, which I leave you as an exercise. It's not obvious. In fact, please try to solve it before next time, because we can discuss it next time. It's really, it should be obvious, but it's not. So it's slightly tricky, but it's really first year undergraduate question. So there's nothing non-elementary there. Okay, so now when we have this finitely many proper subfields, which are all subspaces in K, positive codimension subspaces. The base field is infinite, so we can apply this linear algebraic observation and obtain that there exists T inside K without S. Okay, then T generates a subalgebra. In K, but it doesn't belong to any proper subalgebra, then which is equal to K. So K small of T is equal to K big. We're done. So this was the main purpose for today, but let me give you a bit about Galois theory, since we can now do a lot of Galois theory. Yeah, this is the argument. Yeah, so this. So I thought it's obvious. And then I did the experiment. I asked people in class, when I gave this course of Galois theory, several times whether they know the proof. First, nobody knew the proof, but then I did it several times, like several weeks. And then people either didn't know the proof or they came with arguments which are wrong. So somehow this linear algebra is non-trivial, though it should be trivial. So please solve it. Anyway, we can now define everything in Galois theory. For instance, Galois extension is an algebra which is just multiplied by itself and gives several copies of itself. So definition, K over K small is Galois if K times over K small k is equal to direct sum of several copies of K. It's not obvious. If you know the standard definition of Galois extension, it says that K is generated by a polynomial which has all roots in K, which is completely, it's a product of finitely many linear, it's a product of linear of degree 1 polynomials in K. But it's not clear that, well, it's almost clear, but this definition is better because it doesn't depend on the generator. Yeah, and there are some exercises like prove that this definition is equivalent to the standard one, and then you can ask, what about composites? Can you prove that if you add all roots of a polynomial, this will give you a Galois extension? Since adding roots is a tricky operation, this is not obvious, but it's not hard. I'm not going to do it more because I'm not going to use it. But still, it makes sense to state all Galois theory in that terms. If I need it later, I would repeat everything, but I don't think we will need to use it, Galois theory, in this course any more than we already did. So now we can define Galois group and state the main theorem, of course, without proof. So the Galois group, yeah, there's an exercise that you can take the invariants. So G is automorphisms of K big over K small, and you can say that the G invariants in K big are equal to K small. This is also equivalent to K big being over K small being law. So the idea is that this is because automorphisms of K big over K small is the same as automorphisms of K big times K big over K small over K big. And this direct sum. So there is not that many lots of automorphisms, in fact, but you can classify them because it's a direct sum. So this gives you, and this is clear that if it is so automorphism over K big of direct sum of K, of 0 copies of K is just K. You can exchange them. Okay, this is one. And another is now you can define Galois group, and Galois group is this automorphism group, and state the main theorem of Galois theory, which is a theorem about intermediate extensions. So I'm not going to prove it, but it's still useful. You have K big over K small as Galois extension. And then you can consider then there is bijective correspondence. Correspondence between subgroups G1 inside. So let's call it inside G, which is automorphisms of K big over K small. This is Galois group. So between subgroups of that and subfields. And subfields are obtained as K G1. So it's invariant for each subgroup. You can take the invariant the field of all elements which are invariant under G1. So it's G1 invariant vectors in K. So there's one-to-one correspondence between subgroups and subfields, and there is exercise about Galois extensions. For finite, this is what you wanted. For finite fields. Okay, yeah. Probably I will leave it as it is and won't discuss it now. But it's useful. So if you have a finite extension of finite field, then first you can easily prove that the degree, the number of if you have if you have a finite field Fq over Fp, then Q is a power of P. So this is because it's vector space over Fp, and every vector space, the number of elements in vector space is the degree of the number of elements in your field, because you can have a basis. And then you can check that this extension is actually primitive and is given by x power p. So if pn minus 1 equal 1. So this is all roots of this equation give you this extension. And then you can also find the Galois group, which is just x goes to x power p. Yeah, if it's separable, and they are separable. So non-separable, yeah. Yeah, you just check it case by case for finite fields. You can just prove that so if you have this kind of extension, that every element of this satisfies this equation. But the degree of this equation is precisely the number of elements there. So this equation, it's split. If you put it in this field, it will split onto product of linear terms. So this is why it is primitive, and this is why it is Galois.
Example of non-separable extension.
Thanks. It's a very good question. Last time I told it, but let me repeat it. It's very useful. So you consider any field of characteristic P, say Fp, doesn't matter. Any field of characteristic P will go, and you consider a field of rational functions over it, and you consider its extension. So K over it. No, it will be finite extension. Finite extension which obtained K is Fp of t, and then you add root of power p of t. So you add this, in other words, you take Fp of t, this is rational functions, and you add z, and you take its quotient by z power p is equal to t, or this. So it's funny, but you can easily see it. First, all roots of this equation are the same, because if you have a root of this equation, like say z is the root of this equation, then z minus root of p of t power p, this is equal to z power p minus t. So this is a product of linear factors. And they're all the same. And this is true for all generators of this field. And that immediately implies that trace of any element in this field, because they're all the same. There are p copies of the same element for all lambda inside this K. This is why it is separable. It has zero trace. Non-separable.
The finite field is every separable.
Yeah, yeah, yeah. Mm-hmm. So if you want, this is because in finite field you have z power p is equal to z. I mean power p k. So this is always reducible. This kind of equation is always reducible in finite field. Okay, thank you very much, and see you on Monday.